So he's quite well known in resolving the black hole information loss paradox. And besides that, he has done many important works in string theory. So today he's going to tell us about essentially about the information loss paradox of the black hole in a very simple way. So the floor is all yours, Samir, and we are really happy to have you today. Please.
Thank you. Thank you very much for this invitation. Let me try to share the screen and you can tell me if it's working fine. View, enter full screen.
Yeah, it's perfect.
Okay. Okay, so let me share with you my thoughts on the black hole information paradox. And I understand that the audience here are not expected to be people who have thought about this puzzle. And that's the way this talk is designed. If you have heard about quantum entanglement or been familiar with it, that's good. But even that we will introduce as we go along. And the goal of the talk is that by the time we are done, you should be thoroughly comfortable that you understand the puzzle and the different solutions which people have put forth for it. So if you have questions, please do keep stopping me to ask so that everything becomes clear as we continue. So here is the outline of the talk. We'll start with an elementary introduction to the paradox, and then I will introduce the one issue which causes a lot of confusion even today about how to be resolving this paradox, and it's the issue of small corrections. And that issue of small corrections is then resolved by understanding this thing called the small corrections theorem, which is the main thing I want to get to and explain in this talk. So Hawking gave an argument that black holes violate quantum mechanics. There's information loss, different ways of words, different ways of phrasing the problem. But for a long time, people have been having a feeling that maybe there is some subtle quantum gravity effects, delicate quantum gravity effects that we don't quite know what they are, and they will resolve the puzzle. So it turns out that it is not so. This small correction theorem tells you that whatever argument Hawking made at leading order is actually completely robust. If you make any small delicate corrections to your understanding of the black hole or semi-classical physics or anything, you cannot solve the puzzle. So that is very important because that tells you that the puzzle has to be solved by some big change somewhere. And then in the end, I'll also spend a little bit of time in explaining how I believe it's been resolved in string theory. And that is something called the fuzzball paradigm. And there it turns out the black hole, which has normally got a vacuum around the horizon in the classical and semi-classical descriptions, actually its structure completely changes. It becomes more like a planet or a star. And then, of course, there is no puzzle. The black hole is like any other object, like a piece of coal, and it burns away like a piece of coal. There is no information paradox. Okay, in the end, I'll say a little bit about the other approaches, like the wormholes and so on that people try. But these approaches have, in my opinion, severe difficulties. Okay, so that's the outline. And so let me start by talking about the black hole information paradox. And the origin of the problem is actually very simple. And it comes from the fact that gravity is an attractive force. So here I have taken a mass big M, and here is a test mass little m at a distance r. And we know that in Newtonian gravity, the potential energy is minus g mm over r. And this minus sign is what tells me that the force is attractive. Now let's look at the energy of this mass little m. And even by itself, it has an intrinsic energy, E equals mc square. But if I place it near this mass capital M, then what energy should I assign to this? Let us just work in a hand-waving way for the minute. And so I will add its intrinsic energy and its potential energy and write something like this. Okay, so that's the total energy of the mass little m when it is kept near this mass capital M. But this formula is very interesting because as little r becomes smaller and smaller, this negative term becomes more negative. And at some radius r given by this expression, the total energy becomes 0. And if r is even smaller than this value, the total energy becomes negative. So here is this critical radius. And if I put the test mass closer than that to the mass capital M, then the net energy of this mass, the intrinsic mc square minus the PE, is actually negative. So if you do this properly with general relativity, that's what you should be doing, because once I talk about E equals mc square, I'm talking about special relativity. If I talk about the gravitational potential, I'm talking about gravity. And you know, when you mix relativity and gravity, you must do general relativity. But it doesn't change the answer much. You simply get an extra factor of 2 there, and that sets the critical radius. Later we'll see this is the radius of the horizon of a black hole. But if you're inside this critical radius, this particle has net negative energy. Okay, so the conclusion we have from this very elementary analysis is that if you have a mass which is inside this critical radius, then adding this mass to the mass capital M actually reduces the total energy of the system. You've actually added something, but the total energy has gone down, because when you put two things very close, the negative minus gmm over r, it's more negative than the mc square you paid to create this particle. So that's very interesting, because now it looks like though you can get particles for free. The vacuum is actually unstable in the presence of gravity. So you can keep putting lots and lots of particles till the mass goes down and down, and the total mass of this object, you can make it 0. Maybe you can't make it exactly 0. Maybe you have to stop and it becomes Planck mass. But anyway, something very small. So now it seems you can make an infinite number of these objects, which are all basically either massless or have a very small mass, like down to Planck mass, where quantum gravity may stop your argument. How do I know I can make an infinite number of them? Well, firstly, there are many ways to choose what I choose for the central mass. I could make it a piece of copper or a piece of iron, many ways to choose that. There are many ways to choose what I put here. If these could come in 2 different flavors, like orange and brown, then depending on which one is orange, which one is brown, if I choose n of these masses, little m, there are 2 to the n arrangements right here. But the real kicker is this last one. I can start with an arbitrary big mass, capital M, and then put these masses, little m, till the total mass comes down to 0. And there, since my starting mass could be as big as I want, I can actually make, because of this step C, an infinite number of these guys. For reasons we will see later, these guys are called remnants. They're called remnants, as we'll see, because they're actually produced at the end of Hawking radiation. But these, whatever I'm calling as remnants, are an infinite number of massless or very low mass objects, which I can just produce using just 2 facts: that gravity is an attractive force, which we know is true, and secondly, E equals mc square, which we also believe is true. Now, is there a problem with that? Well, in quantum field theory, if you have a lot of infinite of massless particles, in fact, an infinite number of them, then things go haywire. And why is that? If you have any kind of particle, it can run inside a loop, and it gives a contribution to the loop. And we know that there are such effects are there in quantum field theory. But if the particles are very heavy, then they don't contribute. But whatever the mass might be, if you have an infinite number of particles of the same mass, then the loop integral is going to diverge. In any case, if you have an infinite number of massless or low mass objects, it's very difficult to make a theory which can actually include them. So we have to wonder about whether we are doing the right thing. Is there some way out of this very simple argument? So then let's ask, how come we don't see this problem all the time? We have used something so elementary. Why are we not always stuck in this problem? And the reason is sort of like this. In everyday life, suppose you take something like the Earth over here, and here is the mass little m. When little m is coming close to this capital M, this formula for the potential energy, it works only up to the time you get to the surface of the Earth. Once you're inside the Earth, the potential actually rises more slowly, and it never actually reaches a point where the mc square can be cancelled by the negative potential energy. Okay, so then you might wonder if most of the objects in the universe are never like dense enough to allow you to get close enough in to make the PE sufficiently negative, then maybe it doesn't matter. But this is where the black hole comes in. So what is a black hole? If you start with a star, after it stops burning, then nothing is holding it up. So it starts undergoing collapse. And as it collapses, it's a runaway process, because the denser it becomes, the stronger the pull of gravity. And so it's a runaway process where the whole thing ends up in a point, and then that's what we call the black hole. Okay, so once we have a runaway process and all the mass m has gone to the center, it's gone to a point. Well, in that case, now the whole argument really runs exactly the way we were saying, because inside this entire domain here, this boundary we were talking of, 2gm by c square, that's what we actually now call the horizon, once we have identified this thing with a black hole. And then in all this region inside here, if I put a particle, the mc square of that particle is less than the negative part I get from the gravitational PE, and the problem is back available to me here. So why does a black hole actually undergo runaway collapse? Well, the structure of a black hole in general relativity is the following. So you know that at any point in normal space, you can draw a light cone. Here time goes up and space is the horizontal directions. Then the light cone means that you cannot go faster than the speed of light. Your path of any particle has to stay within this blue cone. It can't go like this. It can just stay in the light cone. But if you have a heavy mass placed somewhere, then this is the angular direction, this outward the radial direction, time is up. Well, with this picture, as you start coming close to a heavy mass, the light cones start tilting inwards. That is the effect of gravity. And normally with something like the Earth, they would tilt inwards a little bit, but you can still go out and you can go in. It's a little more difficult to go out, but you can. Right? So that is the attractive force of the Earth. But if the object is dense enough, then there comes a point where the light cone is actually sloping like this. So if you go in, of course, you can go in, but going out, that is this direction of the light cone, doesn't matter how much close to the speed of light you go, you will still stay at the same radius, and that's the horizon. And if you're inside the horizon, well, all directions point only towards smaller values of the radius r, so you have to keep going in. So that is why you suffer the runaway collapse. Actually, once your object has become inside the horizon scale, then there cannot be any force that stops you from collapsing further, because it doesn't matter what forces you have to actually even stay at one point. Needs you to go outside the light cone. That means needs you to go faster than the speed of light. So as long as everything goes at or less than the speed of light, you have to actually keep collapsing. So how do you know things can actually get to this particular radius where the light cones turn over? Well, at least with classical and semi-classical physics, when you start looking at the collapse of a star, you find that the density at the point where the star reaches this critical value at which the light cones have tipped over is still very low. In fact, the bigger the star you start with, the lower the density is at that particular point. With very low density physics, we think we know the physics. So if no new physics can come in at low densities, when the ball is of very low density, well, then there is no difficulty, it would seem, at least from classical mechanics, that the thing has to keep collapsing. But once it goes inside the horizon, then the light cone structure traps you. You have to go to a point. We call that point the singularity. And then now the puzzle can start again. Okay, so that is how we are actually going to crush things to a point and be able to use this argument of negative energies. And this will happen automatically for a black hole. And that is how black holes get into the story. Okay, but then you could ask, okay, so here's your black hole. Now to make use of this funny things like remnants and make an infinite number of them, somebody has to go and place these particles in the negative energy configuration inside the horizon. So who's going to do that? Nobody actually takes his hand, reaches inside a black hole and puts something there. So if nobody makes them, maybe there isn't a problem. Well, this is what Hawking found in 1974, the thing he is famous for. He showed that in fact, the particles automatically get placed in the correct position with the correct energies because of quantum mechanics. So very roughly, this is the argument. In quantum mechanics, even the vacuum is not really empty. It is always fluctuating. And so here's a toy model of the fluctuation. From the vacuum, for a time, you can pop out an electron-positron pair. Let this be the electron, this be the positron. And that, of course, costs you some energy, like mc square plus mc square, so 2mc square. That's the extra energy delta E. But then you cannot have energy coming from nowhere. You can borrow energy for a short time. So then they re-annihilate after a while. These are called the quantum fluctuations. And you can have a fluctuation of energy delta E as long as it lasts for a time delta T. So that delta E delta T is less than or of order h bar.
Hello.
So that's fluctuations. Was there a question for me?
Yeah, I had a question. I raised my hand, but somebody told me that I should ask directly.
Yes, please. Ask it. I could not see that.
Yeah, I have a very fundamental problem with that picture that you made earlier. When you consider yes, for instance here, when you consider a sort of mass inside this R, this is a very classical concept. We know that in quantum mechanics, there is no, you cannot forever put a mass inside a well, if you like, an energy well. Now you can consider it as an initial condition, but then the wave function goes out. Therefore, in this consideration of R as a limit is a very classical concept. Such a thing does not exist in quantum mechanics. Therefore, I don't know how this concept can completely change if you look at these two mass m, big M and small m, as quantum particles and wave functions, which have an infinite wave functions.
Okay, very good. I think that's an excellent question because agreed, everything here has been completely classical. In fact, very, very elementary and hand waving. But there are two things we should notice here. The first is that all this is happening at very long distances. Like if you take a solar mass black hole, the radius of the horizon is about 3 kilometers. If you take a black hole like those at the centers of galaxies, the radius of that is about 10 to the power 8 kilometers. And in principle, you can take it to be any radius whatsoever. So the whole point is that the semi-classical approximation, which is classical particles up to some little wave packet uncertainties, those rough ideas should still work. But the second point in relation to what you ask is even more important. There will always be small effects due to quantum mechanics. Here, if I talk classically, I'm saying nothing can come out of a black hole because the light cones point inwards. As we will see, the reason that Hawking radiation comes out of a black hole is exactly because classical physics is not the correct physics. It's quantum mechanics. The moment you start realizing that particles are described by quantum field theory, you find that actually radiation does come out of a black hole. The classical black hole does not radiate, but the quantum black hole does radiate, though very slowly. The bigger the black hole, the less the quantum effects, so the longer it takes to radiate. But that is exactly the phenomenon of Hawking radiation that we are going to see in a minute. So you are absolutely right. These are classical claims, and quantum mechanically, which we'll go to in a minute, you will see the radiation come out.
Yeah, but this should also solve then the problem of flavors that you explained, which means the entropy.
So that we will have to see, because what we'll find is exactly the opposite. When we actually see how the particles are coming out of the black hole, we will see that when they come out, they leave behind something which makes those remnants with infinitely many flavors. Okay. So let's just get to that. And that is, so it's very good you asked this question right now, because that's exactly what is going to happen. Every time a particle goes inside and tries to make that remnant, a similar particle is created outside because total energy must be conserved. The outside particle is Hawking radiation. The entire process is quantum, but the particle which is going inside, that is the one which ends up creating the infinite number of flavors. Is that fine for the moment?
Yes, please continue.
Okay, so that was an excellent question there. So now what we're going to do is, we saw that quantum fluctuations can exist for a short time, delta t, and you can borrow energy delta E as long as we satisfy this kind of a relation. But if you are near the horizon of a black hole, then the particle inside has net negative energy. We can take another particle which is just outside and let that have net positive energy, because outside's net energy is positive. And so the total energy can be zero. And if the total energy is zero, then this expression tells me delta t is infinity, which basically means it's an on-shell process. You don't have to borrow any energy to create this pair. The vacuum and this state with the one pair are degenerate, and the wave function just moves to the state with one pair. And so it doesn't have to re-annihilate, and you get these two particles. Well, the particle outside can now just drift out, and that is what is called Hawking radiation. And the particle that is inside, well, that you can see has lowered the mass of the black hole because the net energy of this was negative. So this capital M plus this particle has less energy than M. This guy has positive energy, it just drifts outside. So what we are finding is the outer particle drifts out, the mass of the hole goes down. And so this phenomena is what is called Hawking radiation. So after the net energy of this we have seen is less than the energy of M itself. And again, using E equals mc squared, we now find that the remaining black hole has a smaller mass. If it has a smaller mass, the radius, which was given by 2gm by c squared, is also smaller. So you can see I've drawn that a little bit smaller, but the process then repeats and another particle pair is created. And so the black hole keeps shrinking and the radiation keeps collecting outside. So all the mass is coming out here and the particles are collecting both inside and outside. And again, if you ask what a strange thing is happening here, all the initial mass capital M is in here, and we have added more things to it. And yet the whole thing is losing mass and going down towards zero mass. And the answer for that is exactly, the reason for that is exactly what we said before, that If you have all these masses, they all have their intrinsic mc square, which is positive, but the gravitational energy between them, the minus gmm over r, but that is negative, and it basically cancels it out. So this thing is, in the end, will have a mass which is close to zero, massless or maybe Planck mass. So this is the phenomenon of Hawking radiation. This is what Hawking discovered in 1974. And the scales for this radiation will give us some idea of what we should expect from a black hole. We are not doing the calculations, but the scales we can guess just from physics. If you take a black hole, there's just one scale in the problem, which is the radius of this horizon. We had called it 2gm by c square, but now let me put c and h bar to 1, just makes it easier to talk about it. So for a solar mass black hole, that's 3 kilometers. The emitted quanta, usually we have been talking in terms of electrons and positrons for convenience, but usually the lightest particles will be emitted because it's just like black body radiation. So there'll be massless particles like photons and gravitons. So I can just ask about their wavelength, and their wavelength is of the order of r. There is no other scale in the problem. How rapidly do they come out? Like if one photon comes out now, how long do I have to wait for the next one to come out? There's only one time scale in the problem, and that's the time scale for light to travel from here to here. It's r upon c, but I have put c to 1. Okay, how many particles will come out of the black hole before the black hole disappears? Well, that's also easy. If each particle has wavelength r, it has an energy 1 over r. Again, c and h bar are 1. If my total mass was m, then you can just divide m by the energy of each particle, and you find the number of particles coming out are the mass of the black hole upon the Planck mass whole square. Okay, so for a solar mass black hole, that is about 10 to the power 77. Okay, so a huge number of particles come out. Also, you can see as the hole gets smaller, its temperature is rising, because as r becomes smaller, the wavelength of the particles being emitted becomes smaller. So the temperature actually goes towards infinity as the black hole is evaporating. So if you ask what happens when the black hole has become very tiny, what's it going to do? One logical possibility is it's evaporating faster and faster. So let's assume the thing is completely gone. And then that was what Hawking assumed in 1974. The hole evaporates away completely. But this is what actually leads to our entire puzzle. To understand the puzzle, for a minute, let's talk about the problem of entanglement. So where does entanglement come into the story? When you produce particles from the vacuum, like the one we produced before, we said we get an electron and a positron coming out of the vacuum. They'll annihilate later, but for the moment while they are there, well, the electron can be on the left and the positron on the right, or you could have the positron on the left and electron on the right. And in fact, you will get a linear superposition of these. Okay, so if you have particles like this, when you do the same thing near a black hole, the same thing happens. You will get a superposition. In one case, the electron is inside and the positron is outside, or it can be the other way around. You actually get a linear combination. So if you look at the particle which you have outside and you ask, is it an electron or a positron? You find it is not in a definite state. It is an electron if the guy inside is a positron, and it's a positron if the guy inside is an electron. Well, that's what we call an entangled state. The overall system of what is outside and inside is, of course, has a well-defined state, but looking at just the guy outside, it doesn't have a definite state one way or the other. I have an entanglement between the radiation quanta and the quanta which have fallen into the black hole. So this will be the key issue of the entire problem. Now, this entanglement can come from many sources. Right now, we were talking in terms of electrons and positrons. So we said electron inside, positron outside, and vice versa. So, okay, so from charge, you can see there's an entanglement. If the particles you're emitting are not charged, it could be the spin. Typically, when particles are created from the vacuum in this way, the total angular momentum is 0 because the vacuum has no quantum. So one particle could be spin up, one spin down, and then minus spin down, spin up. So you can see the spin leads to entanglement. Was there a question for me? Okay. So then you might say, what if the particle has neither charge nor spin? Does that still lead to entanglement? And the answer is yes. There's an even more fundamental entanglement in the process of Hawking radiation. And that is because this creation of particles from the vacuum, it is probabilistic, right? If I look at any one given place at one given time, a particle pair may be created there, or it may not be. This is just something which is happening randomly with some probability at every time, at every position. So if I say that at a given time, there is no particle here and no particle here, that is a possibility. We can write it as 0 and 0. Or there could be one particle here and one particle here. Now there's the pair production. I could write that as 1 and 1. In quantum field theory, if there are bosonic particles, you could also have maybe 2 particles here and 2 particles here. Particles always come out in pairs for other fundamental reasons of quantum field theory. So the actual state, just in terms of particle occupation number at this location of space-time and this location of space-time, is unoccupied, unoccupied, plus occupied, occupied, plus occupied with 2 quanta and 2 quanta and so on. So it doesn't matter what particles you are thinking about which are radiating, there's always an entanglement between the outside quanta and the inside. The general nature of an entangled state is that it should be a sum of many terms. Each term is a product, something inside times something outside. But if it's not simply a simple product, but a sum of such products, well, that's where you have entanglement. So what all we have learned from this is that the particle production in Hawking radiation has an entanglement between the radiated particle and the particle which stays inside. So let us introduce some convenient notation. The particle outside, we'll call it B, and the particle inside, we'll call it C. The reason for this notation is there are also particles which don't have much to do with our story, which fell inside to make the black hole in the first place. Those we call A. But anyway, these are the new particle pairs which are being produced. The outside members we call B, the inside members we call C. And when you actually do the calculation, the entanglement between them from all the sources we talked about before, it is order unity. So you can just make a toy model for the entanglement, because whether the entanglement is log 2 or log 4 or order 1, it doesn't actually matter. The argument is not affected by that. So it's simplest to take a very simple toy model for the entanglement. Let it be a normalized state where either both of these modes are either in the state 0, 0 or in the state 1, 1. And here 0 and 1 could mean occupied or unoccupied. It could mean spin up or spin down. It could be electron and positron, some combination of those. It's just a toy model. But anyway you model it, the entanglement between the outside and inside members of the pair is order 1. For this particular description, it is just equal to log 2. And now you can see as I produce more and more pairs, what is going to happen. This B1 is entangled with C1. That's the first pair which came out. So the B1 was the first particle of Hawking radiation. It's drifting off to infinity. The C1 is falling into the hole, and their entanglement is given by this, and that contributes log 2 to the entanglement of the radiation with the remaining hole. But then after a time, another pair came out. The outside member was B2, the inside member was C2, and their entanglement gave this factor here, and that also contributes log 2. After you produce n pairs, n particles collect here, B1 to Bn, and n particles fall in here, C1 to Cn. The whole state is a tensor product of all of these, and then the entanglement entropy of all the outside with all the inside in this simple model is n times log 2. So you can see it is growing with the time. As you emit more and more particles, the entanglement of the outside with the inside is growing, and it keeps growing. So if I write emission steps on the x-axis and the amount of entanglement between the radiation and the remaining hole on the vertical axis, the entanglement just keeps rising in the Hawking process. Now, this is different from the behavior of a normal body. If you burn a piece of coal, then suppose this is an atom near the surface. This may emit a photon, and that's the radiation coming from the burning piece of coal. And the piece of the photon that comes out is typically entangled with the atom which radiated it. For example, if the atom was in a spin 0 state to start with, if it emits a photon with the spin up, then the atom will be left with a spin down, but that is superposed with the amplitude. The photon had spin down and the atom was left with spin up. So the emitted photon and the remaining atom were actually entangled. So as you start emitting the photons more and more photons, the entanglement actually starts rising in the beginning, just like the black hole. But I'm actually trying to make a model like the black hole, where the black hole completely disappears. So I want the coal to go away. So how do I do that? Well, after some time, the remaining atoms here, once the photons have gone from them, will those atoms, let's say, also drift out to infinity like pieces of ash. So then in the end, nothing is left here. But when this atom drifts out to infinity, then in the radiation, I have photons and I have atoms, and they are entangled with each other. So the entire radiation is just entangled with itself. This photon is entangled with this atom, this photon with this atom. This is, of course, just a toy model. In general, everything will be entangled horribly with each other. But the important thing is nothing is entangled with anything which is left behind. Because there's the vacuum, there are no particles there, there's nothing to entangle with. So after about the halfway point, the entanglement of the radiation with what remains behind starts going down. And at the end, when the coal is completely gone, the entanglement of the radiation with what's behind goes back to 0. This is the behavior of a normal body, sometimes called the Page curve, who computed the exact shape of this near the turning point. But the important thing is, for a black hole, it's just keeping on going up and up. And the real difference here is that for the black hole, the new particles which we created, they came out of the vacuum. So the photon did not come out of a piece of out of an atom, which then later I can bring out and make it like this. I created the outside particle just from the vacuum, and the outside inside particles both came out of the vacuum, so they were entangled. But the inside guy just goes in, and because now the net object which I have left inside in my picture of Hawking radiation actually has no, let me just go back to my picture of Hawking radiation. The object here has a lot of structure, but it has no mass. That is not what happened with the piece of coal. In a piece of coal, if you want to have no mass, you have to have no atoms. As you lower the mass, you have to have fewer and fewer atoms. And so in the end, there is nothing there, there's nothing to entangle with. Now, why was it different here? Here, in fact, the number of things inside this, what we call the remnant, actually kept going up. All the initial particles are still here in the middle. More things have fallen. And as we said, the total mass is still going to zero. And that is because of the negative gravitational PE, not because the particles have disappeared, but because they are so close to each other that the net energy can, of the total thing, the MC square parts is cancelled by the negative gravitational PE, and the total mass is going to zero for that reason. So because of this, we are still left with a huge entanglement. And so here is our situation. We have to ask the question, what happens at the end point of the evaporation? So Hawking said the black hole is going to disappear, as we had said. So you start with the black hole, you emit a pair, more pairs, you get to the small remnant, and then, well, all the energy is here. There's no mass here. And Hawking said if there's no mass, there shouldn't be a state. The only state with no energy should be the vacuum. So he said, this is the vacuum. Well, now you have a problem. Because this radiation was highly entangled with this remnant. We said the entanglement was n log 2, and n for a solar mass black hole was 10 to the power 77. And if I just remove this now saying it had no energy, then this radiation is in a highly entangled state, but there is nothing that it is actually entangled with. Now that is actually very strange because there's nothing wrong in two things being entangled, even if they are very far from each other. An electron in the room here can be entangled with an electron on the moon. I can be spin up here and down on the moon, minus spin down here, spin up on the moon. That's completely fine. But if the electron on the moon now disappears from the universe, then I cannot define the state of the electron which I have here in my hand because only the total state actually made any sense.
Sorry, can I make another nasty comment here? You are considering in the Hawking radiation, I mean, in the usual formulation, you're considering only photons or massless particles. But if you consider that, as you said earlier, when after radiation, when the mass decreases, the effective energy or temperature of the black hole increases. Now, when you go to higher energies, higher temperatures, let's say, or energy scales, there is more probability to create massive particles, and this means that for you increase the amount of energy radiation, but you decrease the number of quanta. Therefore, this should, decrease the entropy, because the entropy does not depend on the energy, but on the number of particles, number of states. Can you explain how do you solve this paradox?
Okay, so it's interesting that some of the things you said are completely correct, but one thing is not. So what happens is, we already said that it is indeed true that the temperature of the hole is increasing as the hole is getting smaller, because the wavelength of the emitted particles was just given by the radius. So as we said, as the hole becomes smaller, the temperature becomes higher, but not the energy of the hole. The energy of the hole is actually becoming lower. Because as you know, the whole mass of the hole is going down, overall energy is conserved. So if the radiation particles have carried away some energy, the remaining hole actually has less energy. And of course, as we said before, many times, that magic is happening because of the negative minus Gmm over R. So because of the negative attractive nature of gravity, as we said, everything is because of only that fact. We have a very funny situation that as the black hole loses energy, its temperature goes up. Now, normally, as you gain energy, your temperature goes up. But for a black hole, at least for a Schwarzschild black hole that we took here, as you decrease the energy, the temperature goes up. This actually means that the specific heat of the black hole is negative. And that is a very well-known fact in black hole thermodynamics. The Schwarzschild black holes have a negative specific heat. So the energy is negative, but energy is going down. But everything else you said is correct. As the hole becomes smaller and the temperature becomes higher, it will actually start radiating more massive particles. Low energies is not at large sizes, it will basically radiate photons and gravitons. Once it gets down to the size of a few Fermi, it will actually start radiating electrons, protons. All that is true. And however, the entropy thing is a little different. The entropy which we have here that we are worried about is the entanglement entropy of the outside with the inside, and that is keeping on going up. Whether this was a photon, okay, entanglement was of order log 2. Later on, maybe this particle was an electron, this was a positron, that also contributes about log 2. Okay, so the entropy entanglement just keeps going up. The fact that in the later stages of emission, more massive particles are being radiated, it doesn't make much difference to the argument. But it is true. In the end, more massive particles will be radiated. Okay, so what is the problem?
Samir, yes. Samir, can I ask a question while you're still in this slide?
Yes.
So in between the middle and the bottom diagram. So
yes.
in quantum mechanical case, of course, it need not be that it comes fully to the vacuum, right? The thing evaporates. It could be a remnant. Some remnant could be there. I mean, we don't know what happens when.
Yes.
So is there any contradiction of that? I mean, of course, the phase space size is kind of small in some sense, but that's not concrete, right? So can it not really hold that entropy forever?
So I'm glad you said that, because after saying what Hawking said in 1975, I'm in fact going to come and mention remnants in a minute. So now that you've asked the question, let me just say it. After reaching this stage where the black hole size became a few Planck lengths, people didn't actually know what to do, right? As long as the black hole is big, maybe even a centimeter, you don't expect quantum gravity to be acting, because quantum gravity acts at the Planck scale, which is 10 to the power minus 33 centimeters. So at that time, Hawking's argument has to keep working. You'll produce pairs, you'll keep getting radiation. Once it gets down to Planck size, you don't know. So you actually have two choices. One is what Hawking said, so the evaporation is getting faster and faster, let's assume it blows away completely. But most other people were not happy, and they said once it comes down to Planck length, let's assume that some force, we don't know what it is, some quantum gravity effect stops the further evaporation, and I will left with a remnant. So that's called the remnant scenario, and I will mention that as well.
Okay, thank you.
Very good. So those are in fact the two basic scenarios that you come to from this very simple argument. So why can we not describe radiation by any quantum state? I just wanted to give this very elementary argument. So here are the two particles, and suppose they were, this is the outside particle, this is the inside particle, and suppose they were in a singlet, spin up, down, minus down, up. The whole state makes complete sense. And suppose someone would say the first particle now disappears from the universe. Well, you might say, I can still make a state for the second particle. Why don't I just say it is down like this, and there's a minus sign. So there it is. Okay, electron is spin down, minus electron is spin up. That's actually a state pointing along the minus x direction. It's one of the states of the electron. But actually the same state I can write in a different way. The spin down state here, I can define a new basis where I write it as e to the I theta times spin down. It's a different basis I have taken. And for the spin up, I can take a basis e to the minus I theta times spin up. So the same state is actually also equivalent to this state. There's no difference here, because when you have both particles, you have to multiply the two wave functions. So the e to the I theta and e to the minus I theta cancel out. But now looked at this way, if I make this first particle disappear, I would try to write a state for the second particle that goes like this and this. And you know, this is a different state. For example, if I choose theta equals pi, this becomes spin down plus spin up, and that is spin pointing along the plus x direction. So in fact, the only thing that is clear, because theta can be arbitrary, the only thing that is common to all these states for different values of theta is that the probability of being spin down is 50% and the probability for being spin up is 50%. That's the information in the density matrix, but the phase cannot be gotten. And so the wave function for the remaining state cannot be written down. So it's just a way of concretizing what the problem is. So this in a summary is the entire information paradox. You start with a star, it collapses, but it has a well-defined wave function, psi initial at the beginning. So all that has gone here, so far no problem. Still, whole thing has a wave function. You create more particles, they also have wave functions. So far, still no problem. In the end, suppose you say that this all disappears and you're only left with this, then this cannot be described by any quantum state, as we just saw. And then you have lost quantum mechanical unitarity, because in quantum mechanics, if you start with an initial state, there is some Hamiltonian, doesn't matter how complicated. With quantum gravity, it can be very complicated, but the final state should always have a wave function given in this way from the initial state. And the final state doesn't have a wave function, while the initial state did, we have lost the basic unitary evolution of quantum mechanics. So this was Hawking's 1975 argument for information loss. Okay, but people of course didn't like this very much because you want to save quantum theory if you can. And so they said once you get down to Planck size, the further evaporation stops. But as was just pointed out by Sugata, the amount of entanglement here is going to be very big. There are lots of particles in here. There are about m over m Planck squared, and m can be as big as you want. And so that means this remnant here must have an arbitrary large number of internal states. So now if you have only a Planck mass and a Planck volume, how do you hold an arbitrary amount of states in it? In normal physics, if you give me some amount of phase space, which is amount of momentum range times the amount of space range, then per unit cell of phase space in units of h bar cube, there can be one quantum state. So in general, if you have a given energy bound, the energy is also bounded here, just Planck energy, and the physical space is also bounded, just Planck length. Normally, you would think you can't have an arbitrary number of initial states. Of course, gravity has an opposite sign of the potential, so maybe it's possible. But in any case, when people try to make models of theories which have these remnants, there are several difficulties. And we can talk about them separately, but it is a valid model. And many people in the general relativity community would actually accept this model, that whatever stays in there, in the remnant is there. But just note that these Planck-sized remnants are infinite in number. And that's what we started with our elementary discussion, that when we dial down this thing in our elementary initial example, we saw we get these remnants and there are an infinite number of them. And now we have seen the source of where they come from. They're automatically created when black holes form and evaporate, you get these remnants. But then how do you hold the states in that remnant? So many people came up with models. I think Wald has talked about this kind of a model. Here's your space outside, and then you have this tiny remnant, which is Planck radius here. But maybe inside the whole thing opens up into a baby universe. And then that sort of space there, because you can make the baby universe as big as you like, and then you can hold a lot of stuff in there. So maybe that's what the remnant is like. Then some people conjectured his neck could pinch off completely, and then you were left with a disconnected baby universe. So this is the space we have. So Hawking could have like the vacuum here that he wanted, but there is a disconnected baby universe. And so even though the original space has gone to a vacuum, the radiation could be connected by, would be entangled with the quanta in this baby universe. And that's a large amount of entanglement. Okay, so there are many difficulties with this kind of picture. We can discuss them separately, but this is what is called the remnant scenario, or different versions of the remnant scenario. But note that in all these situations, the evaporation of a black hole is fundamentally different from the burning away of a piece of coal. Because in a piece of coal, there's nothing left behind, no baby universe, no remnant, nothing like this. And these particles just entangle with each other. But now we have seen that no, these particles actually entangle with this, and we have to decide what to do with this. It has no mass, but we don't know what to do with it. And that's the puzzle. Okay, so now we see that, just to summarize what we have said, that both the possibilities for the endpoint of evaporation lead to somewhat uncomfortable choices. Here you lose information, so you violate quantum mechanics. And here you have to decide that you have this whole other thing called remnants, which might run in loops. You've got to stop those problems. You have baby universes that may disconnect. Then can they connect back to you and influence you in some way? That creates a statistical behavior which violates predictability in our universe. So there are all kinds of troubles with the disconnected baby universes as well. So if we don't have remnants and don't have vacuum, what should we do if we don't like any of these choices? So people in fact started wondering, could something be wrong with the simple Hawking argument? So Hawking had done a leading order computation of the entanglement, but there could be sub-leading corrections. And we will take a look at what kind of corrections they might be. And suppose they change the essence of the argument. So then the puzzle could go away. Maybe the argument wasn't correct in the beginning at all. So to understand that, let's take a more detailed look at where Hawking radiation comes from, because so far we have been very schematic. And in fact, it will turn out in the end, the schematic thing is correct. But just to be sure of that, let's take a slightly more detailed look as to where how Hawking radiation happens. So the first thing you might worry about is that as these positive energy members, the radiation quanta are being produced and the negative energy partners are falling in, after some time, maybe these C elements, they fill up this space. After all, the horizon is getting smaller, and they choke it up somehow. And then this becomes like not a vacuum here anymore. If you don't have a vacuum here, then you won't get the normal vacuum fluctuations, and then maybe everything changes. So we should worry about that. But actually, it turns out it's not a worry. It's because I'm only be drawing a schematic picture, it looks like a worry. And to understand that issue, let's recall that the black hole is described by the Schwarzschild metric. And if you're not a person from the GR community, you don't have to worry. We wouldn't be actually using any of this. The only point we need from this is the following. If you look at this metric, you find that if you're outside the horizon, radius bigger than 2m, now I've set G also to 1. Where the horizon radius has 2gm by c squared, I'll put G to 1, C to 1, just easier to write that. So outside the horizon radius, if you want to make a space-like surface, it's just like a space-like surface in this room in special relativity, it's a surface t equal to constant. And you can see the metric has a negative sign for the dt square and a positive sign for the other pieces. But if you go inside the horizon, then you can see that this term becomes negative. So the dt square becomes positive and this term picks up a negative sign. Of course, one of the terms should have a negative sign because the total signature of the metric should be minus plus plus plus. But now you can see that a space-like surface is r equal to constant. Okay, so if I want to draw a complete space-like surface in the geometry, it should be like a t equal to constant surface outside the hole. If this is the horizon, r equals 2m, then, and this is the singularity r equals 0, inside the horizon, when I come, the surface becomes r equal to constant. R equal to constant, I can take something like r equals m, which is halfway between the origin r equal to 0 and the horizon r equals 2m. And now you see a surface at constant radius can be infinitely long. You can see I'm just keeping on going down here like this. This is written in something called Eddington-Finkelstein coordinates. And if you don't know what they are, it's not relevant at all. But I'm just trying to show you the nature of what the space-like slices look like in a black hole. Normally we think that inside a radius r, there's only this much space left. I'll soon reach r equal to 0. But because space and time have interchanged rules, and time of course goes on and on, now in fact it is space that goes on and on. So in fact there's an infinite amount of space inside the black hole. And that's what makes the magic of Hawking radiation possible. So we'll now understand how the Hawking radiation actually works in this picture. But all we need to take away from this picture is that inside the black hole, there's an infinite amount of space. This line, which normally looks like a t equal to constant line, it's actually space-like and it's infinitely long. And all the infalling members of the Hawking pairs, they will actually be nicely spaced out along this infinite space over here. That's why the black hole doesn't choke up. Let's understand a little bit more about where and why Hawking radiation comes. So this is the basic structure of quantum field theory, right? That at every point you imagine there is a harmonic oscillator. You can model that as a mass tied to a spring at every point of the coordinate x. Let me just take one dimension. And then all these oscillators are coupled. And if I want to decouple the oscillators, I can go to Fourier modes. And then in a Fourier mode, if I take the state where all the harmonic oscillators for every Fourier mode of this coupled system annihilates the state, I call that the vacuum. And then if I create an excitation in some Fourier mode k, one a dagger k I put on it, I'll get one particle with momentum k and so on. So particles just excitations of these harmonic oscillators. If the harmonic oscillator is in the ground state, then for that Fourier mode, there's no particle with that momentum. Okay, so that's the simple model of quantum field theory. All the scalar wave equation of quantum field theory is actually just a model of coupled harmonic oscillators. So let's just take two harmonic oscillators for simplicity. And there I have taken one, a left one and a right one. And I'll think of this as the oscillator describing the physics just outside the horizon. And this as the physics just inside the horizon. And they are coupled. And so you just have two harmonic oscillators. And you can solve that problem quantum mechanically very easily. And the vacuum is the state, which is the ground state of the two coupled harmonic oscillators. Now suppose that space is stretched. Okay. In general relativity, space can stretch. And I'll tell you in a minute why it will get stretched. But if the space is stretched, then the two oscillators actually become decoupled because now they are far from each other. So let's just say at some time t equals 0, I start with the ground state of two coupled oscillators, and then at t equals 0, I decouple them. Okay, so here's a natural question. If I start with the vacuum state of the coupled oscillator, and now I decouple them, do I get the state which is the vacuum state of each oscillator separately? Well, the answer is no. It's a simple toy quantum mechanical problem, so you can solve it. What you will get is, to some extent, you will indeed get vacuum of this oscillator and this oscillator. I've called these oscillators B and C for reasons we'll see in a minute. So I could end up with the vacuum of both of them. But in fact, it's a superposition. With some probability, I also get the state where this is in the first excitation and this is also in the first excitation. Then this could be the second excitation, this is the second excitation. I actually get a series like this. Okay, so we'll think of this as being the oscillator outside the hole, this as the oscillator inside the hole. I start with the two modes close to each other. And then, as I'm going to show you in a minute, you're actually going to stretch the space. When you stretch space, the link between them is broken, and the vacuum state is actually no longer the vacuum of the local excitations here and here. Because these particles are far, these two oscillators are far from each other, the excitations here are particles here, the excitations here are particles here. And so now, starting with the vacuum, I've got particles created in pairs, which are actually entangled exactly like the 0, 0 plus 1, 1. This is the well-known phenomenon of particle creation in curved space, and everything we need to know about the black hole Hawking radiation is here. So in fact, there is nothing which the actual quantum field theory tells you, which is not in this simple toy model of just two oscillators. So why is the stretching happening? That's the last thing we need to see. The stretching is happening because it's the horizon. As we said, the light cones outside point like this, but as you come inside the horizon, the light cones tilt over, and inside the horizon, you can only go inwards. So you can see if you're outside the horizon, particles can go out. That's the outside mode going like this. But if you're inside the horizon, even though you're trying to go out, you still end up falling in. So inside trajectories go like this. So light cones, light rays which are trying to go out of the hole, they actually get separated at the horizon. If you're just outside the horizon, you do manage to ultimately squeeze out. If you're at the horizon, you stay stuck there. But if you're inside, even though you're trying to go out, you still get dragged in. As you can see, even the outward ray gets dragged in. And there is the stretching. This part of space across the horizon is getting stretched. You can now see that in the picture we had. If I draw a complete space-like slice, if I'd have this as one slice t equal to constant, this is the normal physics outside the hole. It just moves up and up. The t equal to constant slices in time evolution get later and later. But how do they behave inside the black hole? Well, inside the black hole, as you know, in general relativity, I can make slices any way I like. It's called many-finger time. And I don't want to bring them close to r equal to 0. So I'm not trying to advance them very much here. Inside the hole, this direction is time, and this is space. As we said, space and time interchange once you go inside the horizon, because 1 minus 2m over r changes sign.
Hi, Samir. Sorry, just a quick question. So you say these slices here are space-like, but we have these sort of corners where they curve. And clearly in those cases, if R is time inside the hole, then how can these be space-like still in this case?
Okay, very good question. These are actually space-like everywhere. And that indeed can be checked when I give you the actual explicit mathematical form of these slices. Space and that fact that space and time have suddenly interchanged, those are colloquial words I'm using right now. These are Eddington-Finkelstein coordinates, and the slices are actually space-like everywhere. Okay? So it's not obvious from the picture because it doesn't suddenly change from space to time. And in the Eddington-Finkelstein, it's actually all continuous. And if you actually see it in a Penrose diagram, these are just what are called good slices. In a Penrose diagram, where light cones just point up in the normal way, then they just always look space-like. So in fact, it's very important they are space-like everywhere, particularly also in the connection region.
Thank you.
But now you can see where the stretching is happening.
Samir, can I ask a quick question regarding the stretching? Okay.
Yes.
So even in any place close to any mass, right, GR would say that there's always a relative acceleration. So something like that stretching is even there without the horizon, right?
Yes.
So what is the special stretching here? I mean, the pair production can happen in any curvature, I guess.
Yes. Okay, excellent question. Excellent question. That's exactly what is crucial. You're asking what is different about a black hole. There is some stretching of space-time even for a star, right? Let me just explain this picture and then answer exactly that question. That's very pertinent here. So what is happening here? Where is the stretching? The stretching is because that this section of time just moves up over to this section of time and just advances. There's no stretching here. But the point is because you have to join it to this part, let's keep this part the same for convenience, the joining segment. But this part gets longer and longer. So you're seeing there is a stretching. Okay. So again, you can see the stretching is going on. So suppose this part was the vacuum to start with. After it stretches, it creates a pair. And what happens at the next stage of stretching? If you stretch this again, then this part just moves out. This part just moves in, but because the middle part got stretched, a new pair gets produced. So that is just the model of stretching. This is just a complete space-like slice. It looks like bent over in a funny way here. We just think of it in the actual local coordinate, just like a straight slice, a space-like slice. You take the middle 1/3 of the slice and you stretch it. It creates a pair.
Sorry.
You take the middle 1/3 of that slice, stretch it again. Whatever was on the right moves further to the right. What was on the left moves further out to the left. So they just move away, nothing happens to them. But in the middle, you create another pair. And that is how newer pairs keep coming out. More and more particles keep moving out. These particles keep moving in. So just let me explain the answer to Sugato's question. what happens is that as long as you have a horizon, this stretching will keep going on. Now, if you have a normal, let's say a star starts with radius 6 kilometers and then collapses a little bit and forms a star of radius 4 kilometers. Maybe the sun collapsed and made a white dwarf. The time scale over which and the length scale over which all the stretching happens is just of the order of a few kilometers. If the time scale, if the metric stabilizes again, and it goes from being time independent and back to time independent, but in between, for a time of order 3 kilometers, it was space and time region of order 3 kilometers each, it was time dependent, you produce on the order of one particle pair with radius 3 kilometers. Okay, whatever the scale over which the metric is changing, and the time, let the time and space parts be of the same order, you create of the order of one particle with that wavelength. That has almost no energy. But when you come to a black hole, whenever there is a part with a horizon where the metric has the space and time have flipped roles, there is no way that the metric ever stabilizes. There's no way it can actually ever be such that there is a space-like slice which is not stretching anymore. Put another way, there's no way to slice the black hole geometry so that all the slices are identical. See, if you make any sort of slices such that one slice and the next are all identical, then on that slice, there'll be some lowest energy state. You can call that the vacuum. If the state is not changing anymore, no more particle creation. But the black hole geometry can never be sliced. You can slice it with space-like slices, but you can never slice it with slices which are same as each other. And the reason for that is the continuous stretching. And the continuous stretching is happening because space and time have interchanged roles. And that's why the black hole keeps producing particles till it's completely gone, and the star does not. Does it answer your question, Sugata?
Yeah. Thank you very much. Yeah.
There was another question. Can I answer that?
I wanted to ask just a short question. When you are talking about the stretching, where is your observer? Do you consider it with respect to an observer which is outside the black hole or inside the black hole?
Okay, so any observers will be far outside if you want, but actually here it's very important that observers are not coming into the story. The Blackwood paradox is phrased in only one way, which is that you draw a complete space-like slice and you look at the complete state on that slice. And then there'll be entanglements between particles outside and inside, where that's what I have on this slide. I was just about to say that the outside member and the inside member are entangled, and we can take this as a toy model for their entanglement. So I have to look at the complete space on a complete slice to describe what the problem is going to be. Now, an observer, suppose he says, I only observe this, or I observe this, or I can see here, I can see here. Sometimes people talk about what observers see in the black hole. And I think that's the fundamentally wrong way of thinking about this paradox, because if an observer can see only some part of a space-like slice, he actually cannot even phrase the problem. Like if I have an electron here entangled with an electron on the moon, I have to talk about the state on the complete slice. My observations here actually tell me nothing. So indeed, I'm not talking about any observers, but it's a complete space-like slice. You can put an observer anywhere that you like, but it's not going to be relevant for what I'm saying. Okay, so now let's see what's the issue of small corrections. So now that we have gotten stuck with the Hawking puzzle, we don't quite know what to do with it. People started wondering, they didn't like either of the two options. We don't want the whole to completely go away. We don't want information loss, and we also don't want to have a remnant, suppose. Well then, suppose Hawking's calculation, it basically had these waves and the waves were stretching. I have drawn the waves and the waves stretch. This is now the actual quantum mechanical picture of what Hawking was actually doing. We had the harmonic oscillators, but they were really giving you the waves. So now I've drawn the waves. So the waves are stretching like this, and that's the pair creation. So let the dotted lines be the small corrections. Suppose the red lines were the actual stretching in the Hawking geometry. But suppose there are some quantum gravity effects that we have not thought about, that we don't know about. Could they not slightly modify the evolution? So of course they can. But if they make a small modification, why should we care? The only reason you might care is, suppose the correction is 1% from these quantum gravity effects. But suppose the number of particles you emit, now we know that is very large. Suppose the number of particles you emit is 100. Is it then possible that the small corrections from each pair, but then cumulated over 100 pairs, somehow it completely changes the way we were computing our entanglement, and then there would be no puzzle. So let's be very clear about what that is in concrete terms with this picture. In the leading order Hawking calculation, this is the leading order Hawking calculation, you can see that B1 is entangled with C1, that generates an entanglement log 2. Then B2 is entangled with C2, and B1 with C1, those are the entangled pairs. So on this slice, the entanglement becomes 2 log 2, and so on. So on this slice, we already wrote this state before. It is this entangled state. tensor to this entangled state, and so on. That's the leading order answer. But now, because of these small corrections, the state of each entangled pair may not be this simple. What could it be like? Let's make a small change to it. Let's make a model of the small change. State could be this, plus a small amount, epsilon k is small, times the orthogonal state. Okay, if I want to make a toy model of what I can change the state to, I can add a little bit of the orthogonal state, and so I have done that. So nobody can deny that quantum gravity corrections may change Hawking's leading order model to leading order plus a small correction. And what is epsilon k? Well, we don't know. It could depend on anything. It could depend on what happened at the previous step. It could therefore establish a link, entanglement link between different quanta which are coming out. It could do anything. So in particular, suppose at the first step, we just have the Hawking model answer. But at the next step, it might depend on what happened at the previous step. Now in Hawking's leading order answer, every step was independent, but quantum gravity effects might introduce a small correlation. How do we model that? Suppose at the first step you had 0, 0. Okay, so that's the 0, B1, 0, C1. I've taken that piece, I've written it here. Well, then the other piece, which was the piece for B2 and C2, is not just 0, 0 plus 1, 1. I made it a little bit more of the 0, 0. You see the 1 plus epsilon 1, and a little bit less of the 1, 1. See, so now if I choose the epsilon 1 appropriately, I can say if the first pair was 0, 0, this is the way the second pair got modified. If the first pair was actually 1, 1, then the second pair is modified in a different way with epsilon 1 prime. And there, that's a model of small corrections, and you can't rule this out. But how many correction terms are there? If you see, if I actually take n emissions, you find there are 2 to the n correction terms. Okay, so even if each epsilon is very small, it could be even exponentially small in n. If the number of terms is exponentially large in n, do we actually know how to compute the entanglement? So again, the puzzle in pictures is the following. At leading order, each emitted particle was entangled with its own partner. But with subleading corrections, the whole entanglement structure is more complicated. Everything is somehow entangled with everything else, and the number of emitted quanta is very large, as we have noticed. So if I draw a dividing line here and try to compute the entanglement of everything outside with everything inside, if I take into account not only the leading order terms, but also the subleading corrections, is it possible that the net entanglement of all of these very large number of quanta with this might actually be 0? It may be that the sub-correction terms, even though they are individually small, because there are so many of them, exponentially large number of them, maybe my original leading order calculation was just wrong. So in other words, by the time I get to the endpoint of evaporation, the subleading corrections, if they actually remove the entanglement, then this guy is not entangled and this guy can just vanish. If it's not entangled and if it vanishes, it's not a contradiction. And then these guys may only be entangled with each other now because they're not entangled with this guy. And then it would just be like a piece of coal. And I will get my normal radiation graph for a piece of coal. So secretly, all the string theorists who were not seriously worrying about the information paradox, it's not like they believed in remnants or had a concrete model. They somehow thought that small quantum gravity effects might resolve the problem. We don't know what they are, but since we don't know what they are, and there are so many of those corrections, maybe the Hawking puzzle is not serious. But as we'll see now, that is not true. In fact, what we'll see is that the subleading corrections, in fact, actually cannot remove the puzzle. So let's just go down. I'm almost sort of run out of my time. So I'll just quickly try to give you the small corrections theorem. This is the nub of what I wanted to come to. A full detailed description of this you can find in this review article. But we are now going to actually take the model of Hawking radiation. We'll allow arbitrary small corrections and prove that the entanglement will not come down. If we can prove that, then we have proved something very important. It proves that whatever Hawking was arguing in this semi-classical way where everything was sort of rough and approximate, just making a picture, it's actually rigorous. And so you really have to solve the problem, and you cannot do it by any small corrections anywhere. You have to completely change the physics of the black hole. Okay, so let's try to make a model for this so that we can prove our theorem. So outside the black hole, we can just take outside as some part like 10m. The horizon is at 2m. I take some big radius 10m and say outside that is normal physics. So here onwards, I say normal physics. Around the horizon, it's close to normal physics because I'm going to allow myself these small corrections. What happens deep inside the hole? Well, semi-classical physics still seems to be valid there because this is like a 3-kilometer radius region with low curvature and everything. But we won't even need that. So let's say everything inside the hole here, all these particles fell inside. We don't know what happens to them. They can do anything they want, But of course, the physics here should be some unitary physics, could be very quantum gravitational. We don't care about what falls into the black hole. Okay, so this is the minimum we need, because far outside we need to have normal physics. Let's assume that. Around the horizon, if somebody says that the horizon is just like this room to leading order, it can always have small corrections, but to leading order, it should be like this room. That's what a smooth semi-classical horizon is called. And I'm going to assume that the corrections here are small. That's the only input we need. Then, as we have seen near the horizon, we are going to produce pairs, because these Fourier modes of the field, quantum field theory, will stretch. We already said that. And that's where the small corrections can come. And we are going to make no claim about the physics here, because we don't even need that. Now, this is the notation to set up. The particles, we have already set up this notation. Particle B1 is entangled with C1 at leading order, B2 with C2 at leading order, and so on. Again, I draw this with a yellow line over them, saying I don't actually need to know what happens to them once they go inside. But as you know from your work on entanglement, whatever I do to this, as long as it's unitary, the entanglement of these guys with these guys cannot change. Right? If you have two systems entangled with each other and do a unitary transformation on one of them, that states in that system change, but the entanglement of that system with the other system, but that cannot change. Anyway, this is going to be our notation. The new pair I create, I've created n particles up to now. I denote them collectively by the set B. So B in braces is particles B1 to Bn. And then the next step, which I'm focusing on, is when I create a new pair, I call it Bn plus 1, Cn plus 1. That's the new pair. Okay. So that's my model. Now let's try to actually put in numbers. Numbers means expressions for what these quantities are. What is the entanglement entropy at step n? Well, that's the entanglement of all these guys here with the rest. The notation is that S of something is the entanglement of that set with everything else. So this is the region R equals 10m. Everything outside that I call the outside, the radiation region. I want the entanglement of that with everything else. So what is the entanglement entropy at step n? S sub n is just the entanglement entropy of the set B. No physics here, it is just notation. Okay. Then I create a new pair. This is my system in here. I'm dividing everything at 10m, but right now the pair has just been created near the horizon. Well, all that is some unitary evolution of the system. I'm assuming that quantum gravity is unitary. So if the system is only doing something internally by creating this pair, the entanglement of this outside with this doesn't change. So at this stage, the entanglement Sn at the step of the radiation with the rest is still the same value as B. Well, what about the actual new pair of particles? We create them in this state to leading order. And if you just look at this, the Bn plus 1 is maximally entangled with Cn plus 1, because they are like, spin up, spin down, plus minus spin down, spin up, or whatever way you want to look at it. They are maximally entangled. And so Bn plus 1 is maximally entangled with Cn plus 1. So the entanglement entropy of Cn plus 1, if you compute, it's actually log 2. And if you take the complete set, Bn plus 1 and Cn plus 1 together, well, that's not entangled with anything else. When a pair comes out of the vacuum, the two members are entangled with each other. And that's why you get this, but they're not entangled with anything else. So that's why you get this. Okay, that was a leading order answer. But now let's put in the small corrections. Because the corrections are small, this doesn't have to be 0, but should still be small, smaller than some number epsilon 1, when epsilon 1 is small. And this one, because it was log 2, it could change a bit, but still can't change too much, we'll say. So it has to still be bigger than log 2 minus some epsilon 2, but epsilon 2 can't be very big. So here we are modeling our small corrections. To actually see what they look like in terms of the actual Fourier waves and so on, you can go back to the review article I was saying. But this is the net essence. When you put small corrections on those waves, you can only make corrections to the leading order entanglements by small amounts. But for each pair, this crucial thing is, if each pair changes only a little bit, in each pair we have put in a small correction. The question is whether when we take into account a large number of pairs, can these small numbers accumulate and create an order 1 correction to the entire entanglement? In that case, Hawking's puzzle is gone. Okay, so now we come to the important thing. What is the entanglement entropy at step n plus 1? Well, now this Bn plus 1 drifts outside, Cn plus 1 falls inside. And at this step now, the entanglement of the outside with the inside is the entanglement of the set B plus the Bn plus 1. Again, this is just by definition. These are the particles outside. So what I call entanglement at step n plus 1 is the entanglement entropy of this union set, B and Bn plus 1 with everything else. But everything so far has only been definitions. So where is the calculation? It's all in this one slide, which let's try to just see what happened here. We are actually going to use a very powerful theorem, which is called the strong subadditivity of quantum entanglement entropy. If we have 4 sets, A, B, C, and D, and they're all entangled in some horrible way with each other, the entanglement entropy of A plus B with everything else, that's called SA plus B, and the entanglement entropy of B plus C with everything else, that's SP plus C, is bigger than SA plus SC. It's very non-trivial to prove this, but of course we don't have to prove it, we are simply going to use it. We have to choose something for our sets A, B, C, and A will be the set B, the B1 to Bn quanta we mentioned. Set B will be very simple, just a single quantum Bn plus 1. Set C will also be simple, the single quantum Cn plus 1. Okay, all the things I had in the previous 5 slides are now written here. These were the small correction inequalities. By definition, the choice of each pair had a small correction, and this was the definition of Sn and the definition of Sn plus 1. Well, with this choice of A, B, and C, when you put them in the inequality, I will let you check that at leisure at some point, you find that the whatever was Sn plus 1 is bigger than Sn plus log 2 minus this. Well, that's remarkable because we have proved that the entropy at the next step is more than the entropy of the previous step, and you then add the log 2. In Hawking leading order answer, Sn plus 1 was Sn plus log 2. Now with the small corrections, it can be a little bit less than that, but only a little bit. It doesn't matter what capital N is. The beautiful power of this particular argument through strong subadditivity is that the number of quanta, which is what we were worried about, small correction to each pair could somehow get multiplied with a large number of n to produce an order unity effect, but there's no n here. You have been able to put a bound which just has the epsilon 1 and epsilon 2, and so we conclude that if the Hawking process was to give us this kind of rise in the entanglement, with the small corrections, the rise will still keep happening. The graph cannot turn around, it has to keep rising. Now that's a very strong result because it tells you that if you assume 2 very basic things, the physics at the horizon is just like the physics in this loop, 2 leading order. There can be small corrections. And quanta far from the whole are independent of the whole. Once they leave, they are gone. Okay? We sort of use that, the outside was the outside. Then there's no solution to the information problem. So if you keep a semi-classical picture of the black hole and say that some delicate quantum gravity effects are doing something to help me out, answer is no. You can't do that. So you need an order unity correction to low energy physics at the horizon, and otherwise you cannot solve the problem. Okay, so that was what I wanted to show you in terms of the small correction theorem, but I have gone way over time. So let me ask you what I should do. Should I take maybe 5 or 10 minutes and round off what I was saying, or I could end now and we could just do a discussion on what I have said so far?
You can carry on, that's okay.
I should carry on. Okay, so let me just take 5 minutes to tell you what then the solution is. So far we have seen that we cannot solve the problem because we don't like information loss. We can go for remnants, but they have their own difficulties, which we can talk about. And small corrections are not going to solve the problem. So can we have some large corrections to the picture? And we'll talk about the first world paradigm, which comes up automatically in string theory. So in string theory, you have some fixed object like strings and branes, their couplings, the tensions are all fixed. Nothing can be changed in string theory. So if you want to make a black hole, you have to make it by taking a bound state of these objects. Okay, so if you take a bound state of some branes and you set the coupling to 0, like free particle approximation, you just have a bound state. And you might think the size of the bound state, there's only one scale in string theory, you might think it's like Planck length or string length. But then at that point, you have no gravity also. You removed all the couplings. It's a unified theory. So strength of gravity is the strength of every other coupling. Okay, so now let's turn on the coupling in the interacting theory. Only then I start seeing the gravity and I expect to get a black hole. And my semi-classical approximation suggests I get a black hole with a certain radius, which depends on how many quanta I had in my bound state because the radius should be proportional to the mass. But when I actually do this calculation in string theory, I find something rather different. I find the size of the bound state does not remain Planck length or string length or any fixed length like that. It actually grows with the number of quanta I actually had in the bound state. It also grows with the coupling. And in fact, if you estimate the size of a bound state made of, now these are certain kind of branes in string theory, and you don't of course have to know string theory for this talk. I'm just schematically mentioning what happens. If I have N1 kinds of these branes, N5 kinds of these branes, NP kinds of these charges, G is the coupling. These V and L are sizes of compact dimensions, which I need to use to reduce from 10 dimensions to, in this case, it's 4 plus 1 dimensions. Well, alpha prime is the string tension. A very complicated combination of these gives me the size of this particular bound state. But you can see it's growing with the number of quanta and it's growing with the coupling. And remarkably, the size of this bound state for any number of branes in any coupling is always of the order of the radius of the black hole, which I would expect for that much mass and charge and at that coupling. So that suggests something interesting, that in string theory, somehow you can never squeeze the mass to a point. It always tries to fluff up as you put more and more particles in, such that it is always of order the horizon size, so horizon never forms. But in that case, there'll never be a problem, because our problem was that you actually squeezed everything to a point, and then then you could make these negative energy particles by putting it in here. But if everything always remains like a ball, then you just have something like a piece of coal which radiates from its surface, and then there will never be any puzzle. Was there a question for me? Okay. So then maybe we can just spend a couple of minutes to see how this magic happened with the black hole, with string theory, because we always had these no-hair theorems which said that at the horizon, everything has to get sucked in. Remember, the light course turned inwards. So once you come to horizon scale, there's an enormous pressure pulling you in and everything gets dragged inwards. What is actually going, what I showed you right now was just an estimate for the size of the fuzzball. But if you look at the general relativity construction of fuzzballs, what is actually going on at the horizon, that things are not getting sucked in. Well, this was our picture in 3+1 dimensions. And inside here, if you place something, it had net negative energy. For simplicity, let me just draw one space direction, and then the picture is the same. If I come inside this boundary, which is this horizon distance, then I'll get net negative energy. But now suppose there's an extra dimension. String theory has lots of extra dimensions. Then I have to curl them up into a little circle so that I can come to the 3+1 dimensional world where I don't see the extra dimensions. So this is a small circle. And people have thought of extra dimensions for a long time, but they didn't seem to be doing much, because if instead of a line, I had something looking like a drinking straw, well, the physics seems to still be the same. You can have a mass here. This is the distance at which you will have negative energy particles. You can place something there, still have negative energy. In fact, if everywhere in our space, here in the room, inside the black hole, after the black hole, there was a tiny extra circle riding along everywhere, nothing would change. Well then, however, there is a completely different geometry possible when you have the compact dimension. And what is the new geometry? I'll take the same drinking straw which I had, where one direction was the compact circle, and this was my normal direction X. I cut out the middle piece of this straw, and I throw it away. It's not part of my space at all. Then I seem to have two open ends, and if I come here, it looks like I'll fall into the middle of nothing, but space cannot be like that. What I do is I close the ends of that straw like a drinking cigar smoothly like this. Okay, so that's what my space-time looks like. If an ant comes crawling over like this, it will go back here. If it comes crawling over this way, it will go back here. And this region, which was inside the horizon, which was what the dangerous region was, where I can put all those negative energy particles, is not part of space-time. Now, this was a one-dimensional model. In 3 dimensions, the same thing happens. You take the middle region of this ball, the inside of the horizon, and throw it away. And then everywhere you had a little circle, and as you come close to the horizon, the circle just comes and smoothly pinches off, and there you are. Space-time just looks like this. And what you actually find in string theory is when you do a calculation, you actually take the strings and branes of string theory, you make a bound state, you go to the coupling where you expect the black holes to exist, you find the bound state fluffs up and creates a geometry, which is not the traditional geometry for black hole, which has a vacuum at the horizon and all the mass at the center. It actually has a geometry which is schematically like this. And that's the object we call a fuzzball. So in fact, this game has been done for many years now. It's just like 23 or 24 years old. The idea in the beginning, it just looked like we had a few examples and just an estimate of the size. But in all the work over the last 2 decades and more, one has never found a case where you actually end up creating a horizon. So the fuzzball conjecture says that whatever bound state you take in string theory, you will actually never create a horizon. Everything is like a piece of coal. It radiates from its surface like a normal body, and there is never any problem. Okay, so that's all I wanted to tell you. Let's now just summarize in a couple of slides what we are saying, and then I should stop. This was the classical picture of the black hole. The mass goes to the center, and the region around the horizon is a vacuum that produces the entangled pairs. And then there is a problem. What happens at the endpoint of evaporation? Most importantly, the goal of this talk was to say that no small corrections, no delicate quantum gravity effects between this and that, or that and this, can ever resolve the problem. So the simple argument we made right in the beginning, with Newtonian gravity and mc square, and then slightly more sophisticated language with harmonic oscillators and quantum field theory, That plus a small correction theorem tells you it's rigorous. You do not actually need to know anything about quantum gravity. If the horizon remains like this room to leading order, you're finished. Okay. So then what is the actual solution? Well, there are 5 possible things you could have said, and they are all on this slide. So this is actually my last slide, and I'll stop here. You could have information loss. What is inside could just vanish, give you the vacuum. That's Hawking 1975. But because that's a violation of quantum mechanics, most people are not very happy with that. You could stop at a Planck scale remnant or a baby universe. There's some difficulties with quantum field theory because you get loop divergences, you get ensemble theories. We can talk about that. But if you really want to keep a remnant, you could. Okay. It has difficulties and not very elegant, but we can talk about that. In string theory, it seems that you just cannot squeeze anything inside a horizon. All the bound states that people have tried to make, and a lot of people have worked on lots of cases, you simply don't ever end up making a bound state. You always get something like a piece of coal, and the puzzle goes away. It does need string theory, but I have not put that faked in red, but in blue, because I think that's more like a feature than a bug. String theory has many other positive things about it, because it can reproduce the Beckstein entropy of a black hole. So if we take that as the correct model of quantum gravity, it seems to be automatically solving its problem by just not letting states condense inside the horizon. This is the one that a lot of people are banking on, but we have proved now that that can be crossed out. And this was a desire to have your cake and eat it too. You still keep the vacuum horizon, and you still have therefore normal Hawking radiation, but you hope that some small delicate correction somewhere will remove the entanglement problem. But the small correction theorem we just proved shows that that cannot be done. Okay, so once you knock this out, it's important for the fuzzball game, because even though this was coming out of string theory, people said this looks too radical. We don't want to change the horizon to order unity. Small corrections might take care of the puzzle, and then we won't have to make such a radical change. But now we know that we can't do that. If you don't want fuzzballs for some reason, and you still want a smooth horizon, then you need to have some non-local effects. Because in our assumption, we did assume in our theorem that once a particle left, let's say past r equals 10 m or any given distance that you want, it won't be further modified. No non-local effects. But if you have wormholes, like the kind of thing that Malsina Susskind talked about, or that many of the recent papers are connected to, then you can, of course, take particles from inside the black hole, the ones that fell in, and you can transport them non-locally to the outside. Well, with that, then all bets are off. But that needs very non-local physics, and you can try to resolve the puzzle that way. Personally, I don't think that is actually borne out by anything we can ever find in string theory. But in principle, if somebody says some unknown physics can take the particle from inside and put it far outside, well, then you can remove the entanglement, right? Because the B was entangled with the C inside, where the C can come out through the wormhole and go to infinity. Okay, then you can try to solve the puzzle. There are many difficulties with that as well, but we can talk about them separately. Okay, so that's all I had in the main part of my talk. The recent papers which have been talking about black holes and so on, I had a few slides about that if anybody is interested, but it's getting late, so let me actually pause here. Thank you.
Thank you very much, Samir, for this very exciting talk. And we have had too many questions already, so it seems very interesting topic. So if you have any other question, please ask Samir now.
I have just a question, comment. Huh?
Go ahead.
Yes, please.
Yeah. Okay. In your last slide, you showed that if to solve the problem with fuzzball, we have to have string theory. Especially in your explanation, you have it needs to be sort of one brain and then 5 brain. Sorry, D1 and D5 brains. And we know that there are many observational constraints, a large number of observational constraints, both on existence of horizon and also cosmology from string theory. Now, I don't know if there is any possibility to test your this fuzzball suggestion in practice, for instance, by observing gravitational wave or I don't know, whatever else.
Okay, so let me try to answer that. I have actually written a paper some years ago with Bin Guo and Sean Hampton, where we actually showed it will be very hard to check that the inside of the black hole is a fuzzball. And the reason for that is that the fuzzball structure is expected to go up to only a few Planck lengths outside the horizon. It does have to go up to and a little bit outside the horizon, because if it stops inside the horizon, string theory still satisfies causality. So because the light cones point inwards, doesn't matter whether I have strings there or brains there, they'll all have to go to the origin. Okay? So it has to be slightly outside the horizon, but various estimates about the size can tell you it should go only to a few Planck lengths outside the horizon. But it turns out that light from a few Planck lengths outside the horizon doesn't actually come to us. The gravitational wave detection that we see, all the things that are happening, they are radiation which comes out more from around 6M outwards. Anything which is inside 6M just falls in. So the only part that is used for gravitational wave dynamics is the fact that whatever falls towards the horizon doesn't come back. But if you have at the horizon something which is like at the horizon location, something which absorbs it, like falls into the singularity, or just a piece of coal which absorbs to a high degree everything which is falling in, it'll actually have the same effect. So the gravitational waves which really come out from 6M outwards, the inside part sort of just goes in, they will not be able to show you whether the stuff is actually being absorbed by some degrees of freedom on the surface and then just staying on the surface, or actually falling through a horizon. And if you want to see if light from a few Planck lengths outside the horizon has to emerge to infinity, that probability is very low. The solid angle for light to actually emerge out, if it is coming exactly radially, it can come out, but a solid angle from which, for a solar mass black hole, you can emerge from a Planck length outside the horizon is 10 to the power minus 70. So I think it's not actually possible to see the surface by these methods. One should in fact actually think about cosmology. That's a more interesting way of thinking about what the horizon might be doing. But the cosmological horizon is different in some interesting ways from the black hole horizon. And that is something I've been writing papers on recently. It's something I'm very interested in. So if you read any papers which talk about the vector hypothesis, they're talking about what this whole fuzzball game is doing in cosmology, but that's a different topic. So let me not get into that.
Thanks.
Samir.
Yes, hi.
I have a question which is not maybe your topic that you have covered, but this is like the present hype in solving black hole information paradox using this quantum extremal islands.
Right.
So, yeah. So, could you please comment on that? Like, is it really solved? Whatever their claim is, like, because this fastball is one of the paradigm which trying to explain the thing, and they are right now claiming that this is solved. So what is your comment regarding this?
Yeah, so actually I have read many of those papers in detail over the last year, and actually they are not solving any puzzle there. Their final model is actually a combination of just two of the things on this slide. So they can't do this. This is ruled out, but it's actually nothing more than a remnant scenario. The remnant is being renamed the island. Okay?
Yeah.
So that's all it has. So, and then the non-local effects are being conjectured, but they are not established. So I have some slides where I tried to write that out in case anybody was interested, so let me just try to write that. So people are arguing that by doing something called replica saddle points, you can actually turn the growing entanglement into a page curve, but that is not correct. So I can tell you what they actually do. And the review article of Almeri et al., Maldacena, Hartman expresses this very clearly. This is the picture from their article. And they're actually saying it is just like the remnants, because this is in fact the baby universe picture of the remnant. And they're saying this is what the island looks like, except this is now being called the island. So it is back to the remnant scenario. And the reason is they are simply looking at 2D quantum gravity. With 2D quantum gravity, the black hole evaporation was completely solved in the CGHS model in 1993. And the entanglement just grows. It doesn't come out. So the question is, what could they do new to get something out? And actually they don't. So what they do instead is they say that the entanglement between the outside and inside is growing and growing. So they also know that, right? So how do we make the graph come down? And so what they say is that after the point of halfway evaporation, when the entanglement is really growing high and we actually want it to grow low, let us change the definition of what we call the entropy of radiation. So let me just show you in pictures what they do. So the problem was, this is the original picture of what we had with Hawking. The quanta B, which has come outside, and the quanta C, which are inside, they are entangled, and that entanglement is growing. So that is the puzzle, right? Each of these pairs are entangled as 0, 0 plus 1, 1. What they are now saying is that these outside quanta called B and these inside quanta called C, this is what they call the islands. The island is just the inside part. It's not a new thing. This and this should be thought of as both parts of one system. So when you compute the entanglement of radiation, you should compute not the entanglement of the set B with everything else, and the everything else was basically C. You should compute the entanglement of B union C with everything else. Now, B union C has no entanglement with everything because the particles of B are entangled with the particles of C. So what they are saying is, let's call only this part, which is just near the black hole horizon, as describing the black hole, and the deep inside part, we call it the island. We cannot change any of the dynamics. The dynamics is the same. 2D quantum gravity has no new dynamics. But they are saying that this inside and the outside part should both be called parts of the radiation. The reason they get something from what they call entanglement, wedge reconstruction, and so on, coming from ADS CFT, I do not actually agree with even that part of it, but that's only their motivation. The claim in the end is the following, that this and this together describe one thing called the radiation. And if you define the union of these, whatever entanglement that has with everything else as the radiation entropy, then it will come down. But that is by definition. So the graph hasn't changed at all. So we have simply brought it down by definition. The confusion is caused by the fact that they were not the only people writing the papers. What I like about what Mathur does, at least, is that he's very clear about what he's saying. He's simply saying, yes, I have this island. He draws this picture. He says the things are inside. And then he says there could be non-local effects that allow me to extract information from here to here. There are troubles with those non-local effects because they violate the linearity of quantum mechanics, in my opinion. So we can talk about that separately, but at least Mathur is very clear about the fact that he just has a remnant scenario, possibly with some non-local effects added. But the difficulty is that many people are doing other things in the same set of papers, which are not all the same thing. Now try to write some of them over here. Yeah, why don't you go on? Somebody
I was like not very sure about the other arguments people based on the initial paper that they have written. So it's very confusing, and sometimes people used to say this kind of words. That's why I'm pointing to you.
Yeah. So in fact, I have read all those papers, and it turns out people are doing different things, and that is why it is confusing. So Mathur is changing the definition of what he calls radiation, which he has some reason for the motivation, but in the end, it's a change of definition. And I don't think that's the correct way to do anything. It doesn't solve any problem. It's a remnant scenario. So you have the same difficulties as remnants. Okay? And then you can have non-local interactions like wormholes. He conjectures them. I don't think they are there. But if somebody says they are non-local interactions of quantum gravity, you can't say no. It's up to him to prove it, right? But I think a lot of the papers, for example, the ones by Mathur, which tried to write the Mathur and collaborators, which try to actually give some model for what is happening inside the black hole. If you actually go and look at what is going on there, when they try to change the dot product in the interior, it's actually a non-unitary evolution. So if you have non-unitary evolution inside, it's just like Hawking's information loss. So the way they change the dot product in the interior, it changes the state inside from a unitary evolution to a non-unitary evolution. So separately we can discuss that. Yeah, go ahead.
Hello. Yes, hello. Thank you for your talk. It was really interesting and fuel for a lot of discussion. I was thinking about the Hawking radiation and the creation of particles and antiparticles. Yes. And the way I saw evaporation of a black hole is like those particles and antiparticles meet inside the black hole so that the black hole shrinks due to annihilation inside the black hole. But looking at your diagram, I can see that they never meet, those particles. Am I right?
Let me see if I understand. So are you talking about, let's say, for example, this pair of particles?
Yeah, those pair of particles, but the particle inside the black hole can annihilate with another particle in the black hole, right? Or does it never meet another particle?
Very good. So in the normal semi-classical evolution picture, it never meets the other guy because these guys are well separated by 3 kilometers each and they do not annihilate. However, if somebody were to say he wants to have some completely new quantum dynamics from some source which he is not justifying, but suppose he says he wants to let them annihilate, it turns out it makes zero difference to the actual problem, because any unitary evolution, and I'm assuming it's all unitary inside the black hole, any unitary evolution which mixes these particles up in any way you like does not change the entanglement of the inside with the outside. Mm-hmm. So in fact, when we actually solve the small correction theorem, we actually use the fact that whatever happens in here, I actually grade that area out. I don't care what happens. I'm not assuming semi-classical physics for that. As long as the evolution there is unitary, it actually does not change the problem. So again, just to answer your question, semi-classical physics does not actually make the particles annihilate with each other. That is clear from the semi-classical dynamics. Everything is smooth there, low curvature, so we know what is happening. But even if somebody postulates that quantum reality effects lead to an annihilation, it does not do anything towards resolving the puzzle. Does that answer your question?
Yeah, more or less, yes. Thank you.
Yeah, more questions.
I have a question.
Yeah, go ahead.
So when, exactly like, this is the perfect frame. So when the black hole actually forms and the space-time goes to infinity there, like the space is stretched to infinity.
Yes.
What is the rate of that increase, of that stretch? Or is it like in an instant when the actual center of the black hole is formed?
No, it is not an instant. So what is happening is when the black hole forms, you have a slice like this. In fact, if I put the formation time, it would be something like, a normal slice like this, and just comes out in a scale of, so let the black hole be 3 kilometers. So everything is 3 kilometers on the initial slice. Now what happens is you start waiting on the outside. So on the outside, you wait for times and let every time step be 3 kilometers, just like the crossing time. So let the distance between the successive slices be 3 kilometers. Because there's only one length scale in the problem. Then every time I wait for a time of 3 kilometers outside, the slice stretches by 3 kilometers. And I produce of the order of 1 pair. The wavelength of each of the members of the pair is also of the order of a kilometer. And so these particles are each wavelength a kilometer, and that spacing is of the order of, again, of the order of a couple of kilometers. And as the outside time advances by 3 kilometers each time, the slice stretches by 3 kilometers, and you produce one more pair of particles. That's the scale of the stretching.
Okay. Thank you. And so, okay, so there's the scale. And how would the increase, okay, now actually, I think I'll at least think about this more before I ask. Okay, thank you.
Okay.
Hi. Yeah, so I was just hoping I could quickly clarify something. So in terms of the picture where we have the monogamy paradox and sort of, the arguments that come from amps and so on, as sharpenings of the information paradox, with respect to your fuzzballs, does this mean effectively that this monogamy paradox goes away effectively by ridding ourselves of the interior modes? So we can't be maximally entangled with 2 sets of modes at once effectively. Is that what escapes that? And then on the other side, just about fuzzballs again, you said you sort of really haven't found any bound states in string theory where we don't have horizons. Where we do have horizons. So is this the only evidence we have that sort of these fuzzballs are the typical states? And, because if they're not typical, sort of, how can we guarantee that there won't still be an information paradox with respect to these other states that we've yet to find? Is it proven, I guess, that fuzzball states are typical of generic states for bound states in string theory?
Okay, so let me try to answer the second part first. So it is what fuzzball have managed to do is, if you take the simplest black hole, what is called the 2-charge extremal black hole, you can prove that all the states are fuzzballs. So that's the only black hole which has been completely solved. So I take that as a nice toy model where the entropy formula is of the same kind as the formula for the other black holes. It's like the square root of products of all the charges. And we know all the states, we can construct all of them, and we can prove there are no more. Okay? So at least for one black hole, we know that everything is complete. For more complicated black holes, you cannot make all the states, but that's a little bit like saying you cannot make all the states of Jupiter. Right? Nobody ever tries to make them. But what happened is that as all these years of work on fuzzballs progressed, we started making one state or one family of states or a few family of states of each different kind. So now there are no corners of space left where these other states, which are not fuzzballs, can be hiding. So in the beginning, we only knew states which were actually symmetric. Then the axial symmetry was broken and you could make states which didn't have axial symmetry. Then we had states which were only over-rotating. And then we found states, no, which could be not over-rotating. Then we didn't have non-extremal states, but then we moved into the non-extremal category. Okay? So then slowly, one by one, all the different categories of states, and you can categorize all the states by using the CFT description. Now there's no category left, which could be such that, okay, these guys have regular horizons, and these other guys are special, and they might have a horizon. And that's why I think there is nothing left. Okay? So to answer the first part of what you were saying, actually the AMPS thing was, there was actually no AMPS argument as such. People have talked a lot about the monogamy paradox, but actually they hadn't gotten anything beyond what Hawking had initially. What they're calling the monogamy paradox or the AMPS argument was actually Hawking's original argument. Because Hawking showed that all these pairs are coming out and they're entangled, and the entanglement is rising all the way to the end, so you have a problem. So if you have a smooth horizon, you will get these pairs and they're entangled, so you'll have a horizon. You'll have an entanglement problem. If you say that a smooth horizon leads to a problem, the converse of that is that if you say there's no problem, you want to actually have unitarity, you can't have a smooth horizon. And actually that's all they did. If you go and look at the AMPS paper, if you just go to the second page or third page where they start saying, this is our paradox, they just have Hawking's entangled pairs coming out there. So if A implies B, then not B implies not A. But because they did not do any small corrections, anything, they simply took the original Hawking argument and they phrased it in terms of these bits, which had been used earlier for this small corrections argument. What they were actually trying to do was something quite different. People start talking about the monogamy argument and the fact they have proved something at the horizon, but they were not actually trying to do that, because if you look at that part of the argument, it's the same as what Hawking said. As I just said, Hawking said if you have a smooth horizon, you have a problem. So if you don't want a problem, you can't have a smooth horizon. And they call that the firewall. But that's empty. I mean, it's not anything beyond Hawking. What they were trying to do was tell Susskind that the complementarity argument he was making was incorrect. And that was suspected for a long time. The complementarity argument was not maybe a good argument about how a black hole should behave. And they tried to make a rigorous argument which would shoot down the complementarity. And that they did. Okay? So I think that is the power of the paper. But somehow people forgot about the fact there was a complementarity. There was an argument of complementarity by Susskind and collaborators. And then the AMPS shot it down. Somehow people got confused between the AMPS argument and the original Hawking argument. Because if you look back at it, what did Hawking tell you? He told you a smooth horizon leads to a problem. The same as saying, if you want unitarity, you can't have a smooth horizon. That's exactly what AMPS told you. And if you go back and look at the paper, they have exactly Hawking's leading order computation in there.
Yes.
So I think one should be clear about that.
Thank you. Yes, yeah, I'm happy with that. I agree with that. I suppose what I was asking more was, how would you frame the resolution of the information paradox due to fuzzballs from the point of view that the AMPS argument went? So obviously, of course, they had it all in terms of monogamy. How do fuzzballs solve it from that perspective?
Exactly as you said. You simply don't have this inside region where you can have negative energy particles, so you don't create the pairs. Once you don't have a vacuum horizon, the pair creation at the vacuum horizon is gone, and so you do not have Hawking radiation. So you can actually compute the radiation from specific fuzzballs, and that was done. And it's very beautiful that the rate of radiation comes out to be exactly what is expected from the Hawking radiation, but there are very abstract reasons for that. But on the other hand, the mechanism of the radiation was like a piece of code. You could see the details of the fuzzball coming out in the spectrum of the radiation explicitly, and it's not by pair creation. So that's how the puzzle actually gets resolved. It's not by pair creation at a horizon.
Thank you.
So Samir, I had quite a few questions, but since we have gone over for a long time, and I think I also have to go now. So maybe I will email you, or maybe Anupam can arrange some discussions later on.
Absolutely.
Yeah, it's very interesting talk. Thanks so much. Yeah, thanks a lot.
So maybe I just had one question. Maybe in the remnant picture, maybe can one argue that you do create a remnant, but at some point the horizon disappears. In that case, what would happen?
You mean that's the case where the remnant pinches off? Is that the one you meant?
Not the remnant pinches off, because you still have some horizon left there. But suppose the due to some effect, due to some Planckian effect, maybe the horizon disappears. So then you are the modes are available. Then the entanglement.
Yes. So you can always have, very good question. You can always have what is called a long-lived remnant. Okay, so suppose you stop here, and this place is not a horizon because now this is all Planck scale. So it's, it's just like a normal body at this point, let's say. So you can leak radiation out from here.
Yeah.
Okay. That's called a slow leaking remnant. And this is the kind of model which is there, for example, in the loop quantum gravity papers, some of them. Okay. The difficulty with that is that these remnants can be very slow leaking only. And the reason is, suppose you have n bits of data here. So you have n bits of data to take out in the radiation, right? But your energy is only Planck. So your energy m Planck is shared by n quanta, where n is arbitrarily big. So the energy per photon that comes out is very, very small, right? It's m Planck over n. Now, if the energy is small, the wavelength is very long. Now, if your wavelength is lambda, the particle takes an order of time lambda or more to come out, right? Sure. So you can then say that the bigger the black hole you started with to make the remnant, the longer it takes to actually leak out because of this, because every particle has to be that much slower. So then, in fact, the remnants are so long-lived that any difficulties you had with them running in loops actually are still there for you, right? Because the very big remnants are even longer lived and so on. And so because there were arbitrarily big remnants coming from arbitrarily big n in the beginning, they are arbitrarily long-lived. So any difficulties you had with their existence will still be there. And the difficulties are of many kinds. Like, if we have these baby universes, they can interact back with our real world. So they make everything statistical. You'll be here trying to do an observation, and then that baby universe connects back to you because we can disconnect, it can connect back. And, you get a statistical physics in the lab rather than, predictive physics and so on. So these are what are called ensemble theories. People talk about them recently these days also. So you have all the difficulty of the remnants, but you can actually prove that remnants cannot leak out slowly, and then cannot leak out fast. They have to be slow, and you can put a bound on that, and that leads to the difficulties.
But the unitarity would be maintained.
Absolutely. In any remnant theory, you haven't actually lost the particle, right? The entanglement is the particles with which you're entangling are there, and things can stay there. Unitarity has not been lost. It can radiate away slowly or not radiate at all. You still have your unitarity. Absolutely. Everything apart from Hawking's initial information loss idea, and some of the things which are mistakenly they're doing these days, where they have changed the inside dynamics to actually try to get information out, they're also non-unitary. But other than that, everything is unitary.
Good. Thanks. Thank you very much. So I think you have spoken for almost more than 1.5 hours. You must be tired as well. So I think let's thank Samir for giving such a wonderful talk. And if anyone has any question, you can always contact Samir via email. Please do so. And so thanks. Thank you very much, Samir.
Thank you. This was a great pleasure.
Thank you very much.
Thank you.
Bye.
Bye.
Thank you.